do not add any magnetoresistance, and they may suffer from very high current densities if you have a very thin contact there. And that's actually important even for this ballistic magnetoresistance independently of this, because you put a current through this. Think about it. If you have 10 to the 10 amps through something, that's a huge current. Okay. Okay. So now what I want to tell you is about the origin of the temperature dependence. Okay. So so basically, here it is again. For those of you that don't have very much resistance to listening to talks, and it's already starting to come close to the end of my talk, which is the following: is here it is what I tell you. Is I tell you that thermal smearing, which is an obvious effect that is there in all tunnel junctions, explains 90 or 95% of the temperature dependence. There is no mystery in this thing. There is some temperature dependence which is not known what it originates from, but 90% or 95% of the temperature dependence is explained by well-known, well-established tunneling things. There is no way out of this one. Okay? So here is what the motivation is, that there was all kind of strange temperature dependencies, and so people were wondering, what does it come from? And here it is what you see. You see these curves, and as you see these curves, as you're increasing the temperature, the resistance, notice here there is a sharp structure in this particular tunnel junction, and the structure gets smeared out. It kind of gets rounded off. And the question is, where does this rounding off come? Where does this slight dependency it comes from, and so on. Okay? So this is the main thing actually that happens, is the rounding off of the sharp. So how did we do this? We took these telephones from Motorola and we took them apart. Actually, we didn't put them apart. And then what we measured the I versus voltage for a high temperature and low temperature in the parallel and anti-parallel direction. And see what happens. Okay, that's sort of the trivial kind of experiment. It's not as easy as I'm describing it, but conceptually it's not very easy. And here it is what happens. So here it is a sample that has a low resistance, R times A low, 1.3 kilo ohms per millimeter squared, whatever the hell that units mean. It is a sample with a large, 24 kilo ohms per millimeter squared. And this is in the two situations that you have here. You have the parallel, the anti-parallel, the spin of one electron points up and the other one points down. Here it is in the parallel, both spins point up. Okay? And so now I have to write down some equations, which is unfortunate because I'm going to write down the equations just at the end of the talk, and that's when everybody's kind of trying to keep awake, trying to get themselves from falling asleep. But that's unfortunately, this is when it comes in here. Here it is the tunneling. This is the tunneling, the IV characteristic, how the IV characteristic from a tunnel junction should come. If you look and you ask yourself, how does the tunneling occur? You have to have a denser states on the left-hand side, and there has to be an empty denser states on the right-hand side. There has to be, the barrier height has to enter there, and it turns out the smearing of these denser states here at the Fermi function enters there. At the end of the whole story, you end up with this equation. That the dIdV is proportional to some matrix element which tells you how the electrons move from here to there, tells you the denser states of the left electron, the denser states on the right electrons, and because you're taking the derivative here, which is the sensitive part, then you have a derivative of the Fermi function here. And then there is the second term which I will neglect for the moment, so I won't talk about it. So there's two terms actually. But I neglect this term, and that's what most people neglect, the second term. Okay, so here it is. So t equal to 0, the denser states is sharp. There's a Fermi function there. At t larger than 0, it looks something like this, is smeared there. And so the derivative of the Fermi function is peaked, right? It has a peak. So what we will do is the following: we'll just assume that the low temperature data, which is at 5 degrees Kelvin, is the same as t equals 0. And then we convolute the low temperature data. So this is the low temperature data there. That's the part of the low temperature. And we'll convolute it to df/dv, to this function, which we know what the functional form of that thing is. That's, again, no Einstein for anything that I'm telling you here. This is all trivial stuff if you studied anything about quantum mechanics. Right? So that all you have to know is that this function, when you're at t equal to 0, the derivative of the Fermi function is a delta function. So when you put a delta function there, you just end up with m times n times n. That's it. So you can take the 0 temperature data, which is this one, convolute it with this one, and see what happens. Okay? That's called thermal smearing. Okay? And so independently of anything else, the curve shape, the mechanism, anything, Independent of anything else, thermal smearing must be there. If you increase the temperature, things get smeared, that's it. There is nothing. Already Sherlock Holmes know this. Okay? It's clear. Okay? So there is no way to hear. You can't interpret data without taking this damn thing into account. This is what is totally irritating to people that do tunneling that for a long time. That you go to this magnetism meeting and you find that people actually are reinventing the wheel again. And they do, I'm not going to worry about thermal smearing. Well, you can't. It's impossible not to worry about it. It's right there, it has to be there. There's no way out of it. Okay, so again, what I do is I take the DIDV, the experimentally measure the DIDV, I take the DIDV which I experimentally measure, or I didn't Igor measure it experimentally, and we convolute it to the derivative of the Fermi function. That's it, that's all we do. And we compare that, and now remember that in order to do this, we get a smear temperature here. So here it is what happens. Remember, we neglected the second term. That's important, actually. So there it is. So there it is. We take the zero temperature data and we convolute it with the smearing of the Fermi function. And whether you're in the parallel direction or the anti-parallel direction, it doesn't matter. The fit is excellent. And the thermal smearing has to be there. All right? There's a problem. There's a slight problem actually. The problem is the following, is that this is the temperature that you have to use for smearing. And this is the actual experimental temperature. That's the problem. The problem here is that the slope here is not 1, it's 2, roughly. And it varies a little bit whether in the parallel or anti-parallel direction. What that means is that the thermal smearing temperature that you have to use is not the actual temperature of the junction, and that's a problem. And we had all kind of theories to explain this, but until actually Igor pointed out that we have neglected a term. Okay? We neglect that term, which is that everybody neglects it, so we neglect it. Well, you can't. Turns out you can't. You have to include that term there. Okay? So we have to include the second term. And if you include the second term, then that's it. You're successful. The fit and it's equal to the experimental data. So here it is the thing. Here it is without the second term, that is the fit. You see the fit is excellent without the second term. You don't need that damn second term. So forget about it. And the fit, but there is this problem that the fit that you get twice the experimental temperature. Well, you forget about it. You fit it with the second term and then it's good. No problem. Okay, so you don't do what everybody does in this field, you just kind of include the second term. Okay, so what is the conclusion? I told you that thermal smearing is 95% of the temperature dependence. I mean, whatever is left is this temperature dependence. You see, there is a constant temperature dependence there that we cannot explain. That is not explained. It's not an IV, it's not a temperature dependence. This temperature dependence, this change here, these curves are shifted. And that's not explained. But the rest of it, the change of the shape and how this thing varies with temperature, that's all explained. 95%. And insofar as these curves explain it, I mean, anything is pretty well explained. Okay? And including the second term makes the smear temperature to be equal to the experimental temperature. There's some open question because there is a shift along the VDI axis. And there is some models that you have to use for this, and then there is a lot of models for finite temperatures, but I'm telling you that there is a problem. All these models that have been applied, they have not been applied properly. Because what people did is they applied it to the whole junction without including thermal smearing, and you cannot do that. All right? And this was a big fight over, until, people just gave up. I don't know if they gave up due to my aggressivity or they gave up because it's right, but so they gave up. Okay? And so, there's all kind of theories and how this happens, and I'm not sure what the end result of this is because this has not been solved. Okay, so what I told you now is that thermal smearing must be included independently of what kind of, fancy thing you have, all right? What kind of theory you have, and whatever theories that you have, whichever theory you have is your favorite one, you have to include the thermal smearing, right? So I caution you that if you look into this field, and some of you may have looked into this, you have to be careful. Okay, so what's in the future of this whole field? So there's a bunch of very bright future for this, believe it or not, which is the following things. First of all, you can ask yourself, what happens if you have magnetic states in the barrier? Okay, that's an interesting question that actually was addressed in the case of superconductors. In this case, it hasn't been actually, to the best of my knowledge,